All right, homework 17 is continuing where homework 16 left off, where we're doing that hypothesis testing. Last time we did the z-test, and now we're going to do the t-test and the chi-squared and all of those. Keep in mind, for those of you who may have not gotten everything read yet, we have one-tailed test where you're checking to the left or to the right. We have a two-tailed test where it's a not equal and you're testing both of the two little ends. So on number 1 here on homework 17, we're going to do the t-test this time. It says, it seems these days that college graduates are employed full-time, work more than 40-hour weeks. Data are available that can help us decide if this is true. A survey was recently sent to a group of adults selected at random. There were 16 respondents who were college graduates employed full-time. The mean number of hours worked per week by these 16 respondents was 44 hours, with a standard deviation of 9 hours. Assume that the population of hours worked per week by a college graduate employed full-time is normally distributed with a mean of we can conclude that the mean is greater, or can we conclude that the mean is greater than 40 hours? Use a 0.1 level of significance. This is going to be a one-tailed test. The reason we use a t-test instead of the z-test is because we don't know the standard deviation for the population. We know the standard deviation for a sample standard deviation. So it tells us to perform a one-tailed test because we are going to try to see, can we conclude that the mean is greater than 40 hours? Is the mean greater than 40? Remember, we have our two hypotheses, the null hypothesis and the alternate one. The null always includes the equal sign. Since this doesn't have an equal sign in it, it's our alternate one. Our mean is greater than 40, which means the null hypothesis would be, is the mean less than or equal to 40, right? If it's not greater than, it has to be less than or equal to 40. So, they're going to have you choose what kind of statistic, just like last time, way back when we had class. We used the z-test if the standard deviation was known for the population. We use the t-test if we know it for the sample. And so here we're going to just pick that we're doing the t-test. So, the formula, it's going to look pretty much like the formula for the z-test. Looks like this. T is equal to the sample mean minus the given mean over the sample standard deviation divided by the square root of n. So we got to find those things from our problem, but I zoomed up so you'll have to read on your paper. So, first thing we want to know, or for our formula, is what is the mean of the sample? What is x bar? So if you read through there, for the sample, what is the mean that they tell you you have? .44, exactly. That's what it is. Then we're going to do the mean from the population, which is what we're actually going to be estimating. And that'll be this number here that we're trying to compare it to. Is the mean really 40 hours? Then the S is your sample standard deviation. The sample standard deviation is how many hours? 9. And then N. N, how many people did we survey? 16. All right, so we're going to plug our numbers into our formula. We are going to have 44 minus 40 over 9 divided by the square root of 16. And you can either use your regular calculator to do that or the Alex calculator, whichever one you want to use. To come up with your number, it says we're going to round to at least 3 decimal places.
1.778.
Yep. 1.778 is our test value. So when we're thinking about this, we're going to think about our curve. Our critical value is 1.778. We are testing, is it greater in that section, right? U is greater. We are going to do the p-value. There's two different tests. There's a p-value test and the critical value test. For the p-value test, we are going to then use that p of t thing we worked on before on the Alex calculator. P of t. On Alex, P of t is greater than, right? If this is a greater than, which it is, then we don't have to do the 1 minus. If it's a less than, then we have to do the 1 minus because we're doing the opposite way. P of t is greater than 1.778. And on these ones, when you do the t-test, you had to do the degrees of freedom. On the degree of freedom, it's always 1 less than n. So the degree of freedom is going to be n minus 1. 16 minus 1 means I have 15 degrees of freedom. These ones, it's best to do the Alex calculator. So now you're going to use your Alex calculator. I think you can get to the calculator yet. And you're just going to put that in. .0 or 0.048, yep, is my p-value. The p-value is really a percentage. We were checking, is it at this level of percent or not, right? If the p-value is less than that number, we're going to reject the null. If the p-value is greater than that number, we're going to accept the null. So my p-value, 0.048, comparing it to 0.1, is that less than or greater than? It's less than. If this is a less than, means it's not true, we're going to reject the null hypothesis. That means we're going to say this is not true, this one is true, right? I'm just going to write that in there. Okay? So if it's a less than, you reject whatever the null is. If it's a greater, you accept whatever the null is. So it says then for the question, can we conclude at the 0.1 level of significance that the mean number of hours worked by college graduates is greater than 40? Yes, we're saying it is greater than 40. That was the true statement, right? So yes. Is it greater than 40? Yes, we're accepting that second statement. That was the true one. On your calculator, now because it has degrees of freedom, sometimes your numbers are slightly off, but they should be fairly close to what you got doing the Alex calculation. But on your Alex calculator, we are going to go to the stat function. So hit the stat. And then remember we went cursored over to the tests. And this time we're going to do the t-test. Last time we did the z-test. So we're going to do number 2, which is the t-test. And we have the statistics to put in there. So if data is highlighted, cursor over to stats. Okay? So the U0 is the same thing as the U here. What are we comparing? That's going to be our 40. X bar, 44, what we had there. Sample standard deviation is our 9, that's our S. Number in our sample is 16. Unfortunately, it doesn't give you a spot to do the degrees of freedom, and that's why we always end up a little bit off. We are doing greater than 40, so you want to make sure that the greater than 40 is highlighted. And I like to do the draw one instead of the calculate one, even though the calculate gives you the numbers. But the draw gives you the picture too. Ooh. My picture went clear off my screen. Where did I go? Oh, it's drawing. It's just slow. It's still drawing. So you'll see in the little picture that they have their little curve and their shading greater than, because that's where we were testing. You see our test value is 1.7778. They rounded, they're going to carry it a few more places than we did. They said their p-value 0.479. We rounded it up to 4.8. So it's pretty close, right? So if you want to check your answers, you can check it using that stat function and check the test. You still need to know how to interpret it, but you can check your values. All righty. So number 2 there. A citrus rental is a popular car rental agency that has a history of having too few cars available, so that its available cars are overdriven. The mean monthly mileage over the years for the citrus car has been about 1,550 miles. Recently, though, Citrus purchased thousands of new cars, and the company claims the average mileage of its cars is now less than in the past. I was just making sure I hit record. To test this, a random sample of 10 recent mileages of Citrus cars was taken. The mean of these 10 mileages was 1,467 miles per month. Standard deviation is 245 miles per month. Assume that the population of a recent monthly mileages of Citrus cars is normally distributed. At the 0.05 level of significance, can it be concluded that the mean recent monthly mileages of Citrus cars is less than 1,550 miles per month? So my statement is saying, is the mean less than 1,550? Since that doesn't have the equal in it, that's my alternate hypothesis. My mean is less than 1,550, which means my null hypothesis is going to be my opposite of that. What would my null hypothesis be? The mean is greater than or equal to my 1,550. Exactly. Again, we know because we're doing the t-test that it is the t-test, but we do that because we know the sample standard deviation, not the population standard deviation. So if we know the sample standard deviation, we're going to do the t-test, because when you take the assessment, it's not going to come right out and say, use the t-test. So we need to find the value of the test statistic using our formula. X bar minus the mean over S divided by the square root of A. So in this case, our X bar number is what number there? What is the mean of the sample?
1467.
Exactly, 1467. Then we have the mean that we're trying to compare it to, which is the 1,550. Our sample standard deviation is 245, and then N. How many people did we check? Or cars? We didn't check very many cars. How many cars did we sample? How many mileages did they test? 10. There's only 10 there, yep. And it's going to be 10. One other thing we're going to have later, or may have, is the degrees of freedom. If they do need the degrees of freedom, it's always n minus 1. So if we need to put that in somewhere, our degrees of freedom would be enough. All right, so we don't need that on the formula, but we might need that later. Plugging into our formula. 1467 minus 1550 over 245 divided by the square root of 10, and we're rounding to at least 3 decimal places. Okay, are you using the Alex calculator?
Yeah.
Okay, so we are going to do the 1467 minus the 1550. Then we're going to highlight that and do the divided by. On the bottom, we're going to do the 245 divided by the square root of 10. So when I have more than one thing with adding and subtracting and we want the whole thing divided by something, then we're just going to highlight it. Okay? So we end up to 3 decimal places with what number? Negative 1.071.
071.
Okay? So on this one, we are testing less than. But we're not doing the p-value, we're doing the critical value. When you do the critical value, instead of doing the p of something, you're using that t sub something. Remember we had those 2 different ways of finding the values? So you're going to do t sub, and my test point is this number here. So you're going to use that number there, 0.05, and I think you have to have the degree of freedom. Yes, you do. The degree of freedom is 9. Now, to make this work out right, because I'm doing a less than, I have to do a negative value. So if it's a less than, a left-tailed test when you do your critical value, you want that to be negative instead of positive. And then you're going to punch that into the Alex calculator. Do you see where the T sub is? Right there, yep. You probably want to put a negative in front of that, or at least put a negative on your answer. I'm just going to write, since it's left-tailed, we got to make sure we put that negative. If it was right-tailed, we wouldn't need negative. All right, so when you put that into the Alex calculator, what did you come up with for a number? Yep. Negative 1.833 is what you get. So what they're saying is this line right here is at negative 1.833. You're trying to decide, is this number in that section or not in that section? Where would negative 1.071 be? Would it be over here or over here? Is it bigger or smaller than negative 1.833, in other words? It's bigger, right? Since this is negative? Negative 1.071 would be in this section over here. Okay? This section to the left is this, which is our H1 answer. This section over here, then is going to be our null answer that's greater than or equal to. So, we ended up being in this section with our null. That means this is the true statement, this is the not true statement. I'm going to word that. So, at this level of significance, can we say that the mileage is less than 1550? Can we say it was less than 1550? No, because that was the not true statement, right? We said the true statement was that it was greater than or equal to the 1550. So no, we can't say that. It's not true. Based on our statistics, it's not true. Okay? So, p-value, you check the percentages. You're comparing the percentages. Critical value, you're finding where this line is and then deciding, is my test value, which side of my line is the test value on? Greater than, less than, depending on what you're checking. Where's that? Don't worry, we got a whole bunch of hypothesis testing. Hopefully by the time we get to the last kind, you'll go, oh yeah, now it's kind of making sense. All right, a coin-operated drink machine was designed to discharge a mean of 7 ounces of coffee per cup. In a test of the machine, the discharge amount in 13 randomly chosen cups of coffee from the machine were recorded. The sample mean and the sample standard deviation were 7.01 ounces and 0.21 ounces respectively. If we assume that the discharge amounts are normally distributed, is there enough evidence at the 0.1 level of significance to conclude that the true mean discharge differs from 7 ounces? So this one's a little bit different because it says it differs. If it differs from something, it means that the mean is not equal to my 7 ounces, right? Differs, does not equal. I'm going to have a two-tailed test instead of a one-tailed test because I'm looking for the part in the middle or on the two ends depending on what the question asks. So, this does not include the equal. That's my alternative, I should say, hypothesis. Which means my null hypothesis is that the mean actually does equal 7. Right? The null always has the equal. So if I have one that says differs, my null will be it does equal. My alternative one does not equal. Again, it asks for what type of test you're using. Because you know the sample standard deviation, we know we're using the t-test. So we want x bar minus the mean over s and the square root of n. So the sample mean was 7.01. The mean we're comparing it to is
0.2.
nope.
7.
7. Yep. The sample standard deviation is 0.21, and n is 13, which means my degree of freedom is going to be 12. 13 minus 1 is 12, right? It's always n minus 1. I just do that right away while I'm doing the rest of my numbers because I know I'll probably need it later. So, again, plugging those into the formula. 7.01 minus 7 over 0.21 divided by the square root of 13. That's what we want to punch in. .172. Okay. So when we do this test, we have what's called a two-tailed test. I am going to do my test value, and so I'm doing the p-value, so that tells me I'm going to do the p of t. I am going to do p of t is greater than the 0.172 with a degree of freedom of 12. That's going to tell me the number for this section, which is also going to match the number for this section because there should be the same size if I could draw straight. But first we'll find our number. So, that's supposed to be 0.172, right? So, on the Alex calculator, you're going to do P of t is greater than 0.172 with a degree of freedom of 12. .433, you said? 0.433, which means this one is also 0.433. So when you write down what is the p-value, you're going to add these two things together, or you could just multiply by 2 because it's the same number, because I got the same number on both ends, right? So if I multiply that by 2, I'd have 0.866. And then we're going to compare that p-value to the level of significance. So, 0.866, is that greater than or less than 0.1, which is the level of significance that we're testing? It is greater. Now from the first problem, do you remember, if it was a greater, do we accept the null or do we reject the null? Check your problem number 1 out. I said there in problem number 1, if the p-value is less than my level of significance, we are going to reject the null. If my p-value is greater than the level of significance, we're going to accept the null. It's going to be true for all your hypothesis testing, so write it down somewhere. If it's great or if it's less, then you reject it. Reject the null. If it's greater, accept the null. So we got that it was greater. That means we're going to accept the null statement. The null statement is going to be true. That means the other statement is our not true one, right? So the question says at the 0.1 level of significance, can we conclude that the true mean discharge differs from 7 ounces? Can we say that it differs from 7 ounces? Which one was our true statement? The true statement was that it equals 7 ounces, right? So we can't say that it differs because it's equal to 7 ounces. No, we can't say that it differs. That one was not true, the differ one, right? That is not true. I know these are tricky. All right. Again, I forgot to remind you that if we wanted to check our test statistics, we could check them on our calculator using our stat function, right? So just for fun, let's just check this one. So I'm going to hit stat, cursor over to tests, and we're doing the t-test number 2. We want to use the stats, not the data, so the mean value is the 7 here. So when they ask for first, our X bar value, 7.01. Sample, the 0.21. N was 13. This time we were doing the does not equal the mean, so we want the first one highlighted instead of the greater than we did before. So hit enter on the does not equal, and then go to the draw. And slowly it should draw for you. It's not the speediest of graphing your picture. Oh, we got quite a bit shaded in blue. See, I had too big a gap in the middle. Tells me my t-test value, 0.1717, pretty close to what we got, right? My p-value, 0.8665. So we would have just been a little bit off because we would have rounded up to 7 if we were using our calculator. But I think Alex does let you get a little bit off on the rounding because of some people using technology instead of using the formula. So gives you pretty close to those numbers, right? Now, if you do the critical value, you don't see that, but you do see the p-value if you're doing the p-test, or the p-value there. All right. That is the t-test. It's kind of like the z-test we did on the previous homework 16, if you've had time to look at that. Okay, Hypothesis test for a population proportion. So now we're going to have those proportions in their fractions. It says, a hospital claims that the proportion P of full-term babies born in the hospital that weigh more than 7 pounds is 35%. In a random sample of 245 babies born in the hospital, 103 weighed over 7 pounds. Is there enough evidence to reject the hospital's claim at the 0.1 level of significance? So, their claim, whoa, as I throw that on the floor, is that they weigh more, or that the hospital that weigh more is 35%. Right? That's the percent or the proportion. So when we check this one, we're going to say, is that P really equal to 0.35 or is P not equal to 0.35? I can tell when it asks if it's a two-tailed test instead of a one-tailed test that it should be the equal and the not equal. That'll give you a hint there instead of being a greater than or a less than where you have the one-tailed test. Just a little hint in there. So when we do a population proportion, we are going to do the z-test. And our formula for our test statistic is going to look like this. P hat, which is the sample proportion, minus P, which is the given proportion or percent, over the square root of P times Q. Q is going to be the opposite, or the complement of our P. We'll get to that, over N. All of that's underneath the square root if I can read my writing. So, on this one, P hat is your sample proportion. Our sample proportion here says that we had 103 babies out of 245. Now, if that comes out to a nice decimal, you could change it to a decimal. I just used the fraction when I typed it in, but let's go ahead and check, does it come out nice or not? If you take 103 divided by 245, do you get a terminating decimal or does it just keep going? It's a long one, so then we probably have to use the fraction just so we don't get rounding errors. Okay, P is going to be the percent we're checking against, which is the 35%. Q then is going to be 1 minus P. So I'm going to take 1 minus 0.35, which is your complement. If I have 35% here, the opposite of 35% or my complement would be 65%. Yep, 0.65. So Q is going to be 0.65. What else do we need? We need N. N, how many people did we have? We had a sample of 245 babies, right? All right, so we want for our formula 103 over 245 minus our 0.35, all divided by the square root of 0.35 times 0.65 over N245. When you punch it in your calculator, it should look something like that. The screen looks a little fuzzy, doesn't it? Yeah. Let me push the power cord back in. It usually is that loose. Does that help any?
Yeah. Okay. How do we do this?
All right, so get on the calculator. Clear that out. Okay, we want 103 divided by 245 first. So we're not going to do any of those tests yet. That's coming later. We're just going to do our calculation. So 103 divided by 245. Then on the other, whoops, 245 was our number. Got 25 in there. Okay, click on the side of that. Yep, over to the right. There you go. We want minus 0.35. We're gonna, whoops, just have to hit undo there, or backspace. Okay, now we're gonna highlight all of that because all of that's on the top of my fraction. And then we're gonna put divided by square root. And under the square root, we want 0.35 times 0.65. I'm not sure if you need to highlight this or not before you do the dividing. I would do it just to be on the safe side. Highlight the 0.35 times the 0.65. Nope, I don't want it like that because I want the square root over the whole thing. See, nope. Undo. Try to highlight it without the square root. There you go. Now put the divide by. There's how we want it. 245 on the bottom. All right. See how it looks like kind of what we wrote down? All right. So we get a test statistic of what?
2.31.
We're going to go to 3 decimal places of 2.311. Okay, 2.311. Now this one is doing critical value. When you do the critical value, you're using the sub. But because this is a two-tailed test, and our total level of significance is 0.1, we have to divide that by 2. So we're going to take 0.1 divided by 2 and use 0.05. Each side is 0.05. So when we do our critical value, that's when we're doing the z sub something. Z sub 0.05. So when it asks for the critical value, we did the t-test, we did t sub something. If it is z-test, we're doing z sub something. If it's a one-tailed test, we would just use this number. If it's a two-tailed test, we have to divide it by 2. And so when we do that, z sub 0.05, we don't have to have a degree of freedom since we're doing the z-test. We get what number? So if this number is 1.645, then this number is going to be negative 1.645. Okay? So we want negative 1.645 and positive 1.645 for our critical values. So when we test our critical value or test our point, we're trying to find, does this test value, where does it fit in that section of our graph? Where would that number be? Would it be in the first section? Would it be in the middle? Would it be in the last section? If I have 2.311, where would that fall? It's going to be in the last section. 2.311 is in that last section. That last section is the not equal to part. This is going to be the null where it's equal. This section is going to be your H1, and so is this section over here since I'm doing does not equal. It falls in the H1 section, right? So this is going to be my true statement. This is going to be my not true statement. It doesn't fall in the middle. It falls on one of my two ends. So, can we reject the claim that the proportion of full-term babies born in the hospital weigh more, or that weigh more than 7 pounds is 35%? Can we reject the claim? Is it equal or is it not equal? It's not equal, so yes, we can reject the claim. It's not true, right? We're saying it's not equal, so yes, we can reject. Somewhere in there it says, can we reject the claim? If it would have said, can we accept it, we would have said, no, we can't accept it. It's not equal to 0.35. It's not. Equal, that's right. So can we reject it? Yes, it is not equal to that 0.35. It doesn't land in that middle section. All right, so number 5. Let's see if I find number 5. I'm trying to do 6. A presidential candidate's aide estimates that among all college students, the proportion P who intend to vote in the upcoming election is at most 65%. If 193 out of the random sample of 265 college students express an intent to vote, can the aide's estimate be rejected at the 0.5 level of significance? Perform a one-tell test. We're doing a one-tell test because we're using the word at most 65%. What inequality symbol would be the at most? At most is which symbol? If this is the most, I'd have to be less than or equal to. So my question is it less than or equal to 65%? Since that has the equal to, that's my null hypothesis. Is P less than or equal to 65%? Which means my alternative hypothesis would be what? Is P greater than 65%, right? The opposite of whatever I have for that one. But the null always has the equal. So if they use the word at most or at least, those are going to have the equal sign in them. Okay. Since we're doing a population proportion, we are going to use our z-test. And so, we want the P from the sample minus the P that we're comparing it to over our crazy square root, which they say is P times Q over N. So, the P from our sample, P hat is what they call that. I don't know why they call it P hat, just because that looks like a hat. I don't know. P hat. My proportion from my sample is 193 out of 265 is what they tell me. Again, let's try to see if that comes out halfway decent or is it a great big long decimal. All right, then we'll use the fraction. Our regular P is what we're comparing it to, 65%, right? Our Q then. Q is 1 minus P. 1 minus 65% would give me 35%, right? Yep, so 0.35 is our Q value. And our N value, N is 265, right? 265 were sampled. All right. So, now the trick to get it into the calculator. 193 over 265 minus our 0.65 all over the square root of 0.65 times 0.35 over our 265. Yep. Did you try that one yet, or are you taking the word for it?
How else do you have to do?
On there, you have to hit a bunch of equals in there. So if you're doing it on that calculator, you would do the 193 divided by the 265 minus the 0.65, which is all on the top of the fraction. Then you'd hit equals. Then you're going to take that answer, so you're going to hit second function answer, and you're going to divide that by square root, so you do second function and the x squared to get the square root, and then you do 0.65 times 0.35, and I don't think you need parentheses. I think you can just divide by the 265. We're going to find out. And hit equals. There's our number, right? So you do the top, hit equals, and then do the answer divided by the bottom. All right. We are doing a one-tailed test. Our one-tailed test says we're testing less than. We are going to find the p-value. Now when you do p of z on the Alex calculator, it tests which direction? P of z is greater than, right? P of z is greater than on the Alex calculator. Since we're trying to test less than, we have to do the 1 minus in front. 1 minus p of z is greater than, because we want the less. And the Alex calculator does the greater. 2.672. So you have to keep in mind that when you're looking at that Alex calculator, which way it's testing, most of the tests are all greater than. If you're doing less, then you do 1 minus that.
Is it this P? This one?
1 minus p of z. So we're going to do, yes, it is that one, and we're going to do 1 minus that. 1 minus first, if we want to put it all in at once. Did you get that number already? 1 minus p of z is less than or equal to our test value 2.672 equals, there we go, that's the right number. Did you figure that out? Yours is kicking you out. Password.
So it's, we're gonna do
So we
one.
did 1 minus, and then the p of z, yep, and then our test number 2.672. And hit equals. So, that number 2, 3 decimal places, is 0.004. 0.004. Again, this is a percentage. We're comparing this percentage to the critical value. Here's the critical value. So, if I have 0.004, is that less than or greater than the 0.05 that I'm testing? If it's less than, now we're back to thinking. If it's a less than, do we accept the null or reject the null? Look at your notes. Guess again. If it's a less than, we reject the null. If it's a greater than, we accept. So what we're saying is the percent we got is that it's only a 0.4%. 0.4% is less than 5%, so we can't say it's true. It's not big enough, right? I want my percent that I think it's true to be higher than the percent I'm testing it at. So this percent is not greater than this percent. We can't accept the null. So that means this is not true. This is true. That statement's not true. The bottom statement is true. So can we reject the aide's estimate that the proportion of the college students who intended to vote is at most 65%? Can we reject that? That's the hard part, trying to decide yes or no, isn't it?
Yeah.
I know. So, we are going to reject the null. We're saying this is not true, so this is true. We're saying P is greater than 65%. So can we reject that it's at most 65%?
Yes.
Yes, we can, because we're saying the other thing is true, right? So yes, we are rejecting that first claim. We're saying that first claim is not true. I know, it'll take some practice. It took me a while to figure it out, for sure. All right. Number 6. A psychologist specializing in marriage counseling claims that among all married couples, the proportion P for whom her communication program can prevent divorce is at least 77%. In a random sample of 220 married couples who complete the program, 165 of them stay together. Based on this sample, can we reject the claim at a 0.01 level of significance? Perform a one-tailed test. We know if it's a one-tailed test, it's going to have the greater than or the less than, not the not equal to one. So, the claim is it's at least 77%. At least, that's another one of those, at most, at least, all those. If it's at least 77%, at least 77%, what inequality symbol represents the word at least? Greater than or equal to, right? If I said you gave me at least $100, you gave me $100 or more, right? At least 77%, we're going to say greater than or equal to 0.77. Again, because that does have the equal, that's our null. P is greater than or equal to 0.77. The alternative there, alternative one is P is less than 0.77 then. Again, since we're doing a proportion, we're going to use the z-test when we do our test statistic. And then we got to use our formula. So, P hat minus P over the square root of P times Q over N. P hat, our sample proportion, is 165 over 220. P, the percent that we're comparing it to, is 0.77. So Q is going to be 1 minus 0.77, which is going to be 0.23. I'm trying to write the 3 first. 0.23. And N is going to be 220. So we're going to take those numbers, plug them into our formula. 165 over 220, I'm not even going to worry about if it comes out nice. We know how to get it typed in. Minus 0.77 all over the square root of 0.77 times 0.23 over 220. Yeah, negative what?
0.705.
Yep. Negative 0.705. All right. So, on this one, the H1 section is the less than. Right? So what we're doing is we're checking the left side. We're doing the left-tailed test. This is our critical value. When it ever asks it for the critical value, that's when you do the sub. So we're doing Z sub, but we want the answer to be negative because we're doing the left side and not the right side. So we're going to do negative Z sub point, what was it, 0.1. Again, if it was a two-tailed test, we would divide it by 2, but since it's a one-tailed test, we use that number. If we're testing to the left, we use negative. To the right, we want a positive number. So you're just going to do negative Z sub 0.01. Negative 2.326 is what you got? Okay, so that means that this dividing part is at negative 2.326. We want to decide what section our test value is in. Is our test value less than or greater than that number? The test value is greater than that number, right? The negative 0.705 would fall in this section that's greater than, which means this is the true statement, this is the not true statement. So now the weird question at the bottom. Can we reject the psychologist's claim that the proportion of married couples for whom her program can prevent divorce is at least 77%? Can we reject this claim? No, we can't. That's the true statement, right? So no, we can't reject that. That's the true one. All right. Hypothesis tests population for variance and standard deviation. You have to remember that the variance is the standard deviation squared. Sometimes they give you the standard deviation, and if you need the variance, you just square it. Sometimes they give you the variance. If you need the standard deviation, you would take the square root of it. So those two things work together. The variance is the standard deviation squared. It says the human resource department of a major corporation announced that the number of people interviewed by the corporation in 1 month has a mean of 104 and a variance, the standard deviation squared, of 233. The management of the corporation suspects that the variance exceeds 233. A random sample of 18 months yielded a mean of 99 interviews with a variance of 441. If we assume that the number of people interviewed by the corporation in 1 month follows an approximately normal distribution, is there enough evidence to conclude at a 0.1 level of significance that the management's claim is correct? What was their claim? Their claim was that the variance exceeds 233. The variance is the standard deviation squared. If I exceed something, I'm going to be, what math symbol? Greater than 233. Okay? So, that doesn't have the equal. We know that's our alternative hypothesis. The standard deviation squared, or the variance, is greater than 233.
Are we on homework 17?
Yes, we are. Number 7, day 17, way up there at the top, it says that.
I don't have that one.
It should be with your 16 that we did last time, so maybe you pulled it out of your notes. 16 and 17 were together, but we only did one homework page because we did our assessment. So we did 16, but we didn't get 17 done.
This one, right?
There's 16. Did I have to print that for
Yeah,
you?
you had to print.
Yeah, I'll probably have to print this one for you too, because then you must have been missing both of them, I'm gonna guess. Let me print that quick here. All right.
Thank you.
Yep. Oop. Now we'll see if it wants to write exceeds greater than 233. That should kick out here in a minute. It's got to warm up probably. So if we know the alternative hypothesis is that our variance is greater than 233, that means the null hypothesis would be the variance is less than or equal to 233. The null always has the equal and would be the opposite of whatever that one is. So it just depends on our statement. We are doing a one-tailed test. Our one-tailed test is checking, are we greater, because we always compare it to this, to the 233. So my alternative hypothesis would be in that section, my null hypothesis would be in that section that I'm trying to test. Again, we are going to do, if we're doing standard deviation, the chi-squared test. The chi-squared test, I can't remember if it had the word or if it had the symbol, is the one that looks like x squared, but it's really read chi-squared. So I can't remember, but for some reason I wrote the degree of freedom down there. So it might have chi-squared and then you might have to put the degree of freedom. I can't remember for sure which way you have to do that. We'll figure out what the degree of freedom is in a minute. So when we are doing our test statistic to find chi-squared, we are going to do the standard deviation squared, which is actually your variance, times n minus 1 over the population standard deviation squared. So you have your sample standard deviation squared, or your variance of your sample, and sample variance. And then you have the population variance. So, in there it tells me my sample variance. I have a random sample of 18 months, yielded a mean of 99 with a variance of 441. That's the sample, right? So my sample variance, my S squared, is at 441. The population variance is going to be the one that they gave you.
Wait, is
That
that,
we're
is that,
oh, I said 441 and I wrote 444, didn't I? That won't work very well. Let's fix that. Thank you. 441. So my population variance, that other weird symbol, is going to be the one that you have in your problem. Just like on the regular mean. So it's going to be the 233. What else do we need here? We need n. N is 99, right? There are 99 interviews, right? N. Wait a minute. Never mind. If I read the question right. In a random sample of 18 months, we had a mean of 99. My sample was 18 months. There's my n. N is going to be 18. So I mentioned earlier when you do chi-squared, just like when you do the t-test, you have to do the degree of freedom. Whenever you do the degree of freedom, it's always n minus 1. So my degree of freedom is going to be 18 minus 1, which is 17. I think they have it where you have to pick out the symbol chi-squared, which looks like x squared, and then you put the degree of freedom of 17. Otherwise, I don't know why I would have written that down. In my formula, then, for my test value, my sample variance was 441. I'm going to take that times the n minus 1, which is 17, and I'm going to divide that by the given variance that I'm comparing it to, which is the 233. So at least that one's easier to type into your calculator. What did you get when you put that in there?
I don't know if this is right.
It's a little bit off because you put 223 on the bottom and we were supposed to have 233 on the bottom.
Oh, I
Try it again with the 233 down there. But it is kind of a big number.
Is it 32?
Yep.
176?
Yep. 32.176 is our test statistic. So, we are going to do a p-value test. So that means on the Alex calculator you're using the p is greater than, right? The p is greater than, and we're doing chi-squared. Now again, because we are doing a greater than here, we don't have to do the 1 minus. If it was a less than, we'd do the 1 minus. So we're going to just use p of chi squared is greater than, or 32.176 with a degree of freedom of 17, right? And that's going to give our percentage we're going to compare it to. What do we get when we calculate that? So keep in mind, if it's a greater than, we just use the p of whatever. If it's a less than, 1 minus p of whatever, just like on our other tests.
Zero,
0.014, yep. That's what we should be getting. We are going to compare that to the level of significance, right? Whenever we do the p-value test, we're comparing our percentages. Our percent that we came up with was 0.014. We're testing it against 0.1. Is that less than or greater than? It's less than. So if that's a less than, what do? We reject the null, exactly. Reject the null. That means the null is not true, and the alternative is the true statement. The true statement is that my variance is greater than 233. Now we got our weird question. Can we support the claim that the variance of the number of people interviewed by the corporation in 1 month exceeds 233? At least it says the not reject thing. I don't hate it when it says that. So, can we say that the variance is greater than 233? Yes, we can. That was our true statement. Our true statement says our variance is greater than 233. So, yes, we can support that claim. All right. Number 8, IQ scores. IQ scores among the general population have a mean of 100 and a standard deviation of 14. A researcher claims that the standard deviation of IQ scores for males is less than 14. A random sample of 19 IQ scores for males had a mean of 102 and a standard deviation of 9. Assuming that the IQ scores for males are approximately normally distributed, is there significant evidence at the 0.05 level of significance to conclude the researcher's claim is correct? What in the heck was their claim? The researcher claims that the standard deviation is less than 14, right? See that sentence there? So this one we're doing standard deviation, not variance. And so my standard deviation symbol is that crazy one that looks like that. And the claim is it less than 14, right? That's what it says, is it less? Which means on our one-tailed test, we're testing to the left. Again, this does not have the equal in it, so that's my alternative hypothesis. Is it less than 14, which means it goes in there. That means my null hypothesis is my standard deviation greater than or equal to that 14, right? My null hypothesis, that'd be in that section over here then. So, on our formula says we're taking s squared times n minus 1 over the standard deviation squared. Notice we just have the standard deviation. So we're actually going to do the squaring as opposed to when they give me the variance, I just use the number that's there. So that's why they did them both kind of together. So in this case, S, my sample standard deviation is 9. So that means in my formula I'm going to do 9 squared. I'll jump to the n. My n. How many people did I have in my sample?
102.
No. A random sample of
100.
how many? 19, right? So we did a random sample of 19 scores. The n is 19. Gives us the mean. We don't even need the mean in this problem. It gives us the mean, but we don't need it. So we're going to do 19 minus 1. In other words, 18 there. Over, and then our standard deviation, the one from the problem, is 14, right? And so on the bottom, we're going to do 14 squared. If you want to make it easier to type in, you could just do the 19 minus 1 in your head. Oh, I forgot to pick out my test statistic. My test statistic is the chi-squared. The degree of freedom is my n minus 1. So my degree of freedom is going to be my 18, right? Probably should put that in there. So my degrees of freedom, n minus 1, 18. So we're going to do 9 squared times 18 divided by 14 squared to find the value of our test statistic.
No.
7.439. Okay. 7.439. I wrote 2 different things there. Now I'm trying to figure out which one was the one I wanted. I think it's the bottom one. So, we are doing a left-tailed test, but we're doing this critical value. On the critical value, because this is over in this section, the 95 or the what percent are we looking at? 5% would be this section, and we want this section. When we do the critical value for this one, we are going to do the chi-squared, and we're going to do 1 minus that critical value. Instead of just using the 0.05 like we normally get to do on the chi-squared, if we're going to the left, we're going to do 1 minus that with a degree of freedom, of course, of 18. So I think you can either type it in with the 1 minus, or you can just do the 1 minus in your head and just put in the 0.95, whichever way you want to put it in there. That's why I wrote 2 things, I think. So you're going to do, since I'm doing a critical value, the chi-squared sub. Oops, yours keeps going to sleep on us, huh? See the chi-squared sub on there? It's that one. Yep, that one right there. And you can either just put in the 0.95 or 1 minus 0.05. And my degree of freedom is 18. Yep. All right. So, we get 9.390. That means this value right here is 9.390. That's my critical value. So keep in mind when it does the critical value, if it's a left-tailed test, you got to subtract that. If it was a right-tailed test, then you could just use that number that was there. But left-tailed, you got to do 1 minus that. Kind of like the P thing. On this then, my test value is 7.439. Would my test value fall on the left side or on the right side of my critical value? On the left side, right? My test value, 7.439, falls in this section. So that means it falls in the section of our alternative hypothesis. So that's going to be my true statement. This is going to be my not true statement then. The true statement is that my standard deviation is less than 14. So, can we support the claim that the standard deviation for males is less than 14? Yes, that's my true statement, right? My true statement says yes, it is less than 14. I like it better when it says support and not reject. Support's easier to figure out. All right, one last one on this page. Number 9. A new sleeping pill is advertised to increase the daily sleeping times of insomniacs by an average of 2.9 hours with a variance of 0.35. The government group conducts an independent study on the new pill claiming that the actual variance of increase in sleeping time is different from the advertised variance. The government group tests 20 insomniacs chosen at random with the new pill. The insomniacs report a mean daily sleeping increase of 2.9 hours with a variance of 0.57. Is there enough evidence to conclude at the 0.05 level of significance that the government group is correct? Assume that the increase in the sleeping time provided by the new pill is normally distributed. Notice it says perform a two-tailed test. If it's a two-tailed test, it's not a greater than or a less than, it's a not equal to, right? Anytime it says it's a two-tailed test, I'm testing not equal to. So is my variance not equal to the 0.35, which is what their claim is? So again, when I pick out where does that go, the equal has to go with the null. So is my variance equal to 35% or is my variance not equal to 35%? And again, this is a two-tailed test, so I'm going to have my H1s on both ends and my HO, my null, in the middle. Since we're doing a variance, we're doing our chi-squared. We have to put our degree of freedom in there, but we haven't figured that out yet, but we can. The degree of freedom is n minus 1. N, how many people did we survey on this one? 20, and so n minus 1 would be 19 for our degree of freedom. Since n is 20, 20 minus 1 is going to be 19 for our degree of freedom. All right, our formula that we had S squared times our n minus 1 over our variance squared. So our sample variance says we have what? What's the variance from the sample?
So,
0.57, exactly. 0.57. That's going to go in for our S squared. Again, it gave us the variance, so we don't square it when we do our formula. If they give you the standard deviation, then we have to square it. So we're just going to use that 0.0, or is it 0.57, if I write the right thing down. 0.57 times n minus 1 would be our 19, right? That was our degree of freedom, over the sample, or the population variance. The population variance is the one from the problem that we're trying to compare it to, which is our 35%, right? So we're just going to take 0.57 times 19 divided by 0.35. And again, it's kind of a big number, or bigger than what we have been used to getting anyway. Yep. 30.943. Okay, we are doing a p-value. Anytime it says p-value, we know we're doing the p of something on our computer, right? When we do p of our chi-squared, again, it's testing to the right. So we're going to find this number here, which will match with this number here. So on our LX calculator, we're doing p of chi-squared is greater than our 30.943 with a degree of freedom of 19. .041, yep. 0.041. So if this is 0.041, that also means this is 0.041. Which means our p-value, we have to add them together or multiply by 2, right? My percentage, if one side is 0.041 and the other side is 0.041, then it's going to be 0.082, right? We're looking at a percentage. Now we're comparing that percent to our critical value. So 0.082, how does that compare to the level of significance? 0.05. It's greater than. And if my p-value is greater than my level of significance, what do I do? We accept the null. Accept that the null is true. So that means this is my true statement, this is my not true statement. Or my false statement, I suppose. Can we support the claim that the variance of increase in sleeping time using the new pill is different from the one given, whatever that says down there, from the one advertised? Can we support that it's different? No, we can't, right? If it was different, this would be the true statement. We're saying it's the same, it's equal to that. So can we support that claim? No, we cannot. Can't support the claim. That's the toughest part, is this part down here. At least for me, that was the toughest part. Trying to figure out the true, not true. Is it this answer or this answer? And how weird do they have that worded down there at the bottom? Alrighty. I am going to let you work until about 4 o'clock. We may or may not get through the next homework page, but I've rattled your brain enough for a little bit anyway.
You do this for me? Thank you. What's on this?
Oh, is that other one? I'm just canceling that, 'cause you just did the midterm and got that done. And you probably haven't done any work on your pie chart since then, I'm assuming.
So I just log out and then log back in?
Yeah, just give me a second here.